Greetings, guys. We're going to talk about sequences in this thing. Now, sequence is really something you learned about in Math 3 and then again in Math 1010. But a sequence really is a lot like a function, except the domain is just your positive numbers. So in other words, the only thing I can put into it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on and so forth. So, for example, we're going to get loose. Well, for example, this is a sequence. This is read S sub n equals 2 times n minus 1. Okay? This is sequence notation. The sequence S with the input n. So if I was going to put a 1 in here, 2 times 1 is 2. And 2 minus 1 is 1. So I would say that S sub 1 is 1. And this is how we notate this. This is the sequence S when the input is 1. So what this is asking for is S sub 2. Well, S sub 2, put 2 in there. 2 times 2 is 4. 4 minus 1 is 3. This is S sub 3. 2 times 3 is 6. 6 minus 1 is 5. Now, do you see the pattern? 1, 3, 5, 7. Good. That's S sub 4. S sub 5 is 9. And S sub n is 2n minus 1. Okay? Every term, every number in that list is called a term. And if I was to express that sequence, I do so with a list of numbers. 1, 3, 5, 7, 9, ... There we go. And I say, there's S sub n. That's it. If I was to graph this on a XY coordinate plane, where I did the input and the output, it would just be a series of dots, not connected. Okay? So there's the idea. This is a discrete relationship where it doesn't take every value in the domain. It only takes 1, 2, 3, 4, 5, and so forth. Okay, moving on. Let's look at this. We'll start with basics. A sub n is 3n squared plus 1. Write the terms of the sequence. So a sub 1, that's just telling you to put 1 into that formula. Well, if I go 3 times 1 squared plus 1, that gives me a 4. A sub 2, that's saying put a 2 into that formula. So 3 times 2 squared plus 1. 3 times 2 squared is 4. 3 times 4 is 12. 12 plus 1 is 13. A sub 3, well, 3 times 3 squared plus 1. 3 squared is 9. 3 times 9 is 27. 27 plus 1 is 28. And I can continue that. Now I'm going to type it in my calculator. 3 times 4 squared plus 1. 49. That goes there. A sub 5, put 5 into that formula. 3 times 5 squared plus 1. Type it in, I get 76. This is one that's harder to see and describe with the formula, but there it is. And there's the first few terms of my sequence. Now, the first 5 terms of this sequence means I'm going to put 1, 2, 3, 4, and 5 in there. If I put 1 in there, I think, B sub 1 is going to be 2 times 1 plus 1 all over 2 times 1. Well, that's going to be 3 over 2. I think I'm going to have to put another 2. B sub 2 is going to be 2 times 2 plus 1 over 2 times 2. Well, 2 times 2 is 4 plus 1 is 5 over 4. What about B sub 3? B sub 3, that's going to be 2 times 3 plus 1 all over 2 times 3. I'm seeing something. The top's 1 more than the bottom. Okay, 2 times 3 is 6. 6 plus 1 is 7 over 6. Hey, look at the pattern. 3, 5, 7. Next one will be 9. 2, 4, 6. This will be 8. Next one, 2, 4, 6, 8, 10. And this will be 3, 5, 7, 9, 11. Oh, so I see a pattern there, but it comes from that equation. Okay, so this is that sequence. Okay, cool, moving on. Here's some examples of sequences. 1, 4, 9, 16, 25. This is perfect squares. So this would look like a sub n equals n squared. That one they can get a formula. This 2, 3, 5, 7, 11, 13. Wow, do you recognize that? If you could find, well, this is the sequence this, n such that n is prime. This is your list of prime numbers. If you can find an equation for that, you're not going to be able to. They've been trying to for the last couple thousand years, and nobody's found one yet. And actually, there's been a really good proof of why there is not a formula. There have been people that believed there was. Anyway, that's a history of math. It's kind of really fun to look at, though. Prime numbers were a big thing for quite a while for lots of number people. This one, this is probably the most famous sequence. This is called the Fibonacci sequence. Featured in things like the Da Vinci Code. There we go. This is a Fibonacci sequence. It's formed, I got to go back. It's formed by this, n such that n sub 1 equals 1. N sub 2 is equal to 1. And then anything n sub n greater than 3 is going to be equal to, a sub 1. There we go. A sub 2. And then a sub anything n greater than 3. So in other words, anything third term or more is equal to the term that came 1 before it plus the term that came 2 before it. Anytime you see this notation that I just wrote, a sub n minus 1, a sub n minus 2, a sub n minus 1 means the term that came 1 before that term. N minus 2 means the term that came 2 before. So the third term is formed by taking the term that came 2 before it plus the term that came right before it and adding them together. So it starts out 1, 1, and then 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8, and so forth. Cool. When you see this, write the nth term. That means write the formula, which sometimes is easy, sometimes is not. But let's look at this. First thing I want to look at is I want to turn this into a fraction. 1 over 1. Well, that 1 at first, because everything else is fractions, so I might as well. And I noticed something. All of those fractions have a 1 on top. So a sub n equals 1. So I'm going to put that there. I don't know if that's right, but I'm going to. Now, the numbers on the bottom, 1, 3, 9, 27, they're all multiples of 3. It's really tempting to go 3n, and that's probably my first guess. But then if I put in a 1, 3 times 1 is 3, 1/3. 3 times 2 is 6, 1/6. That doesn't really work. So I'm going to erase that. But I think multiples of 3, more than that, they're powers of 3. Hey, maybe it's 3 to the power of n. Well, if I put a 1 into there, 1 over 3 to the 1 is 1/3. That gives me this, the second term. If I put a 2 into there, 3 to the second is 9, 1 over 9. So if I put a 2 in there, it gives me the third term. So I can do this, n minus 1. There, that'll give me the term that came 1 before it. Now, other people in class came up with this, 3 over 3 to the n. Both of those are valid expressions of that sequence. So look at it. If it's one of your more traditional things you know how to do, linear stuff like that, you should be able to. Otherwise, you might just have to take a guess, look for some patterns, and check some things like that. Okay, let's look at some other stuff. One thing you see in sequences oftentimes are factorials. You've seen these before. A factorial of a number means the number times the number that came 1 before it, times 2 before it, so forth, until you get down to 1. So, in other words, 3 factorial is 3 times the number that came before it, 2, times the number that came before it. 3 times 2 times 1 is 6. 5 factorial is 5 times 4 times 3 times 2 times 1. Now, all of your calculators have a button on it. My calculators, they're this button right here. It's right beneath your mode. It's like shift, and you'll see that factorial. So you could do that. But worst case, I just go 5 times 4 times 3 times 2 times 1, and I get 120. Okay? Now, 10 factorial, yikes. That's just 10 times 9 all the way down to 2 times 1. Wow. I can go 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Takes me half a second, and I get 3,628,800. Or I can find the button on my calculator and go 10 factorial, see it there? And hit equals, and I get the same thing. Now, 0 factorial is 1, period. Okay? If you'd like to know why, ask me in class. Or Google it and look it up. Why is 0 factorial 1? Okay? I'm not going to go into that in this video. However, 8 factorial over 5 factorial. I want you to notice something. 8 factorial means 8 times 7 times 6 times 5 times 4, all the way down to 1, right? 5 factorial means 5 times 4 times 3. Wait a second. You see how 5 is going to cancel, 4 is going to cancel? In fact, everything will cancel except for this. So if you have a factorial over factorial, think, well, 8 minus 5, that means only the top 3 numbers are going to count. And so 8 times 7 times 6, that gives me 336. Cool. Now what about this? Now E, you could type that in your calculator. If you type F in your calculator, it's going to give you an error because it's too freaky big. Okay, 85 and 82. Well, 85 is going to be 85 times 84 times 83 times 82 going down. 82 factorials, all that. So that 85 and the 82, everything is going to cancel after 82. And all I'm left with this is 5, 4, 3, 2, 1. Now I can start reducing this, or I could type that in my calculator right as I get. I get 85 times 84 times 83 all over 5 times 4 times 3 times 2 times 1. I guess I could have put 120 because I had that right there, right? Anyway, I get 9,877 halves. Or if I want to do that as a decimal, 4,938.5. But the point is, these factorials, some of them will cancel. Okay? Okay. Moving on. Now, a recursive sequence. A recursive sequence is one where I don't put in 1, 2, 3, 4, 5. My inputs are the previous term. So like a sub n minus 1, that means a sub 3 minus 1. Suppose if you're trying to find the third term, or a sub 2. A sub n minus 1 means the previous term. A sub n minus 2 means the term that's 2 before. A sub n minus 3 is the term that's 3 before. But really, all we're going to see is n minus 1. So in a recursive sequence, I've got to know the first term. So example 4, it says a sub 1 equals 2. And this says a sub n equals 3 times a sub n minus 2. So this is saying 3 times the previous term minus 2. So this is going to be found by going 3 times 2 minus 2. Well, that's 4. The next term is going to go 3 times 4, which is 12 minus 2. That's 12. No, it's not. Dummy. Not you, me. 3 times 4 is 12. 12 minus 2 is 10. Then I go 3 times 10. That's 30. Minus 2 is 28. 3 times 28, yuck. 3 times 28 minus 2 gives me 82. And I go from there. Okay? That's it. A sub 1 equals negative 3. A sub n equals this. Find C of 4. Now, if this was a normal sequence, I would just put 4 into here, but I can't. I've got to put the third term in there so I can find the fourth term. So I've really got to find all the terms, right? Yeah. So a sub 1 is negative 3. The second term is made by 2 times the term before plus 4. So if I go 2 times negative 3 plus 4, that gives me negative 2. And if I go 2 times negative 2 plus 4, that gives me 0. And if I go 2 times 0 plus 4, I don't know why I'm even typing that in. That gives me 4, and so forth. So that should be an A. A sub 4 is equal to 4. Okay, that's a recursive sequence. Now, the big thing that we've looked at, well, the stuff we looked at here, factorials, sequences, that kind of stuff, recursive, that's all 1010 stuff, or Math 3 stuff. This is the 1050 stuff, summation notation, often called sigma notation, because it uses the Greek letter sigma. That's what this big looking thing here is. It's the Greek letter sigma. Now, summation notation, what that does, or sigma notation, is it takes the sum of a sequence. It takes a sequence and it adds the terms together. That's what it does. And there's 3 components in this. There's the sequence itself, so the formula. That's what's right here. This is where you start taking your summation, and this is where you stop. So if I was going to look at this A, this is saying use the sequence n squared, start by putting a 2 in there. So if I put a 2 in there, I get 2 squared. And then I keep going, 3 squared, 4 squared, 5 squared. And there I stop because I started at 2, I stop at 5. Okay? And then I add those together. And that's it. 2 squared, that's 4 plus 9 plus 16 plus 25. I'm doing the squarings in my head, and I get 54. Okay? That's all there is to it. This is saying start with the first term and add through the third. So I'm going to add 3 terms. So 2 times 1 squared plus 1 plus 2 times 2 squared plus 1, okay, plus 2 times 3 squared plus 1. So I got to figure out what all these are. 1 squared is 1, 2 times 1 is 2, plus 1 is 3, plus 2 squared is 4, 2 times 4 is 8, 8 plus 1 is 9, plus 3 squared is 9, 2 times 9 is 18, plus 1 is 19, and 19 plus 9 plus 3 make 31. Okay, cool. 3 to 6 factorial. Yikes. That means I'm going to add 3 factorial plus 4 factorial plus 5 factorial plus 6 factorial. I'm going to just type that in my calculator exactly like it looks. Wow. I could figure it out by hand, but I don't want to. 3 factorial plus 4 factorial plus 5 factorial plus 6 factorial gives me 870. Now notice this. K is 1 all the way to n. So that's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 all the way to 1 over n. Wow. How do I do that? Because n is big. In fact, it's infinitely big. Well, here's the deal. If n is infinitely big, then 1 over n is infinitely small, which means it's equal to 0. So this eventually will go number plus number and get effectively to 0. This does have a sum. If you have a sequence like this that converges, in other words, it ends up ending at a 0, it's getting smaller and smaller and smaller. Any sequence that's getting smaller and smaller and smaller and smaller and smaller and smaller and smaller is said to converge. And any sequence that converges to 0 has an infinite sum. We'll talk more about those, but not today. Let's keep going on. The sum of this, the sum of 4 from 1 to 4, there's no variable. Well, that makes it easy because the first term is 4. Second term is still 4. Third term is 4. Fourth term is 4. And 4 plus 4 plus 4 plus 4 equals 16. There. Okay. So let's take a look at writing it backwards. If I was to express this as a summation, I'm always going to start at 1. Okay, and this one is easy, 1, 2, 3, all the way to 9. So I'm going to go up to 9. And the formula, which sometimes is not easy, is n squared. That's it. This one, wow, summation, n to 1. And this has 1, 2, 3, 4, 5, 6 terms, so 6. But now I got to come up with that. -1, 8, -27, 64. These numbers are something I should Oh, I recognized it. These are perfect cubes. This is 1 cubed, 2 cubed, 3 cubed. Well, what about the negative alternating? Well, that's a negative n cubed. -1 cubed is -1. -2 cubed, wait, is -2. So that's not quite it. The n cubed will give me the number. Oh, but check this out. Oh, wait, it's not n cubed. It's not n cubed because that's 1 cubed, 2 cubed, 3 cubed, 4 cubed. I see it. I see it. I still got to get that negative. What this is, no, it is. It's n cubed. Okay, that will give me the number, but then the -1 to the power of n. There it is. Anytime you're switching from negative to positive, you're going to have -1 to a power. That's it. That's how those work. Because -1 to the first power, that's a negative. -1 squared, that's positive. And so forth. Excuse me, I'm yawning. That's terrible. Okay, now, I'm going to be honest. You're going to see some formulas for sums of sequences in here. I don't know these formulas. I don't memorize them. Okay, I lie. I know this one. I know this one, that the sum of a number n times is just that number times n. I know that one. But these others I don't know, but they are nice to know. Okay, it gives you formulas. If I'm adding the sum of just a number, I get this. If I'm adding a sum of a number squared, I get this. Sum of a number cubed, I get this. Let me show you why it's useful. Suppose I did this. And here's some rules that are nicer to know. This is equal to 3 times the sum from 1 to 10 of k. If there's a coefficient there, excuse me, I can pull it out. Well, I have a formula for this, right? It's right up here. This is going to be the sum of k is n, which here is 10 times 10 plus 1, which is 11, all over 2. So if I do that, 3 times 10 times 11, all divided by 2, I get 165. Cool. This one, the sum of k cubed plus 1 over 10. Well, I can actually split this up. The sum from 1 to 10 of k cubed plus the sum from 1 to 10 of 1. Well, I know this. This is a formula, right? This is n, which is 10, times, I'm looking at this formula here, 10 plus 1, that's 11, all over 2, quantity squared, plus the sum from 1 to 10 of 1, well, that's just 1 times 10. Oh, if I get that in there, 10 times 11 squared, 10 times 11 divided by 2, excuse me, is 55 squared. 55 squared is 3,025 plus 10, that's 3,035. So the formulas are nice when I have things like this. Now imagine this. This is the sum of k squared plus the sum of a negative. Oh, check this out. I can even break this further. I was going to say sum of a negative 7k, but what if I do this? And I know that my summation symbols are getting a little ugly. That's okay. From 1 to 24. All of these are 1 to 24, so I'm just not going to write that down. Maybe I will. Plus the sum from 1 to 24 of 2. Well, this k squared, that's this formula right here, where I take n, which here is 24, times n plus 1, that's 24 plus 1 is 25, times 2n plus 1. Well, 2 times 24 plus 1 give me 49. So 25 plus times 25 over 49, all over 6, minus 7 times the sum of k, which is just n, so 24, times n plus 1, which is 25, over 2, plus the sum of that, which is just 24 times 2, which is 48. Okay, if I get those all together, 24 times 25 times 49 divided by 6 minus 7 times 24 times 25 divided by 2 plus 48. I just typed that on my calculator. I get 2,848. Okay, this one, another one. I can go 2 times the sum from 1 to 10 of k cubed. So more importantly than I think than the actual formulas are, I can pull a 3 out of that summation. I can separate a summation of a sum into the sum of summations. I can separate the difference of summations into the summation of differences into the summation of differences summations and so forth. So the 2 right here I can pull out. And I get 2 times this. Well, there's a formula for that. That's this whole n times n plus 1, that's 11, all over 2 squared. So I can type that whole thing in my calculator. 2 times 10 times 11, all divided by 2, quantity squared, gives me 6,050. So the formulas are nice when I'm dealing with things that I can break apart, and then rather than find the summation of a whole bunch of terms and do it one by one, I can use a formula to do it. But again, I don't have that as memorized. I usually just start plugging things in and going from there. Okie doke. This is sequences. Next time we'll deal with a specific kind of sequence and series, an arithmetic or an arithmetic series. Guys, see you next time. Bye-bye.